All right, so tonight we're going to review for our exam, which starts tonight at 11 o'clock, which is kind of bizarre. So basically it goes for Tuesday and Wednesday of this week. So the deadline is taking it by 11 p.m. Mountain Time on Wednesday. Just some other basic details about the test. There is a 4-hour time limit on the test, but that's more than enough time typically for you to be able to take the test. I would say like the average time to take it is about an hour to an hour and a half to take the exam. So it should definitely not take you the full 4 hours. Something to note though is that once you open the test for the first time, then your timer starts and it doesn't stop even if you shut down the window. So you can save your answers and come back to it, but it has to be, you're still bound by the 4-hour time limit. So if you start it and then you go have lunch or something and come back, then that'll work. But if you start it and then you go to work for 8 hours and you come back home, like your 4 hours is going to be up and you're going to be sad. So, so don't start it until you're ready to actually sit down and take it. There's 38 questions on the exam. You're allowed to have one side of one page of notes with you, which you can write whatever you want on there. And then you can use the Excel worksheets that we've used in class. Pretty much for this exam, there's just the one quantitative descriptive statistics Excel sheet that we've used so far. And then of course you can use the normal probability applet that we've been using to do calculations, and a calculator and scratch paper. And please save your scratch paper and kind of label your problems on there, because later if we go over your exam and you're trying to figure out where you went wrong, then super helpful if you have that scratch paper handy. All right, so we're just going to kind of start back from the beginning of the semester and work our way all the way through lesson 8. We talk about all the different things that we've learned about review, all the different concepts. So starting with population versus sample. So the population is the entire group that we want to draw conclusions about. And the sample is going to be the subset of the population that we actually measure. And kind of going along with that, when we talk about parameters, parameters are numbers that describe populations. So they would be a number that would be calculated from everybody in the population. So some examples of parameters that we've talked about are mu, which is our population mean, and we've talked about sigma, which is the population standard deviation. So these numbers would be parameters, and if we, to find the value for those numbers, we would have to actually measure everybody in the population. And then statistics are numbers that describe samples. So these are going to be numbers that we calculate from a subset of the data, from our sample. So some examples of ones that we've talked about are like X bar, which is our sample mean, or S, which is our sample standard deviation. N, our sample size, is a statistic. The 5-number summary or the median, like any of those numbers would be considered a statistic. So here's a little example. Florida played a key role in recent presidential elections. Voter registration records in February 2014 show that 39% of Florida voters are registered as Democrats and 35% as Republicans. You use a random digit dialing service to call 250 randomly selected Florida residents. Of the registered voters contacted, 34% are registered Democrats. Okay, so looking at these numbers here, starting with this 39% here, is that 39%, is that going to be a parameter or a statistic? So if you think it's a parameter, then give me a thumbs up. And if you think it's a statistic, then give me a thumbs down. How about that? All right, so I think you're all wrong. So, or maybe I forgot how the hand things. I'm trying to figure out if I told you, if I remembered right what I told you for the hand signals. Okay, so the 39% came from all the voters registered. So they had information from everybody in the population. So because they had information on everybody in the population, this number came from the population. So this number is a parameter. Does that make sense? All right. So similarly, this 35% is also going to be a parameter because it was calculated from everybody in the population. So most of the time, it's really hard to get measurement, to have actual numbers from the population because it's really hard to measure everybody in the population. But in this case, you know, is a case where you do have a list of everybody, all registered voters, or like when they do a census every 10 years, then that's another case where they are able to measure everybody. Well, they attempt to measure pretty much everybody in the population. So numbers from censuses, is that the plural of census? Censi? From censes, then they would be considered parameters. Okay, so this other one down here, the 34%, that came from the 250 randomly selected Florida residents. So that one is going to be a statistic. All right, so next we talked about categorical variables versus quantitative variables. And if I'm trying to decide whether or not a variable is categorical or quantitative, I basically ask two questions. So the first question I ask is it a number? And the second question I ask is, would it make sense to talk about the average, whatever it is? So would it make sense to talk about the average? I'll just put fill in the blank with the variable name. So if the answer to both of these questions is yes, then it is a quantitative variable. And if the answer to either of these questions is no, then it's going to be a categorical variable. So this can be helpful. There's some, and there's some on this list even, we'll get to them, that can be a little bit tricky. Some people choose the wrong one, but if you ask these two questions, you'll choose the right one. So, so for this one, I can see all your little video screens over there. So if you think it's categorical, then make a C, and if you think it's quantitative, then make a Q with your hand. So starting with eye color, do you think that's categorical or quantitative? Okay, categorical, yay. Okay, height, is that categorical or quantitative? All right, good job. So that one's going to be quantitative. How you feel about statistics on a scale of 1 to 10? Is that categorical or quantitative? Okay, nice job. That's also quantitative. Income, categorical or quantitative? Perfect, quantitative. Okay, favorite ice cream flavor, is that categorical or quantitative? Categorical. How about age, categorical or quantitative? Good job. So age is something that usually or sometimes tricks students, because on some surveys they kind of turn it into a categorical variable where they'll group ages together. But remember, like, never assume anything on an exam. Like, only just take what they've given to you. So if you think about age in general, is it a number? Yes. And would it make sense to talk about the average age of people in our class? Yes. So that would make it quantitative, which you guys all guessed the right answer, so you were good. And then number of times you've been to Disneyland, is that categorical or quantitative? Perfect, quantitative. You guys are going to ace that section on the exam. All right, so then we talked about collecting data, and there's two basic methods for collecting data. We can do an observational study or an experiment. In an observational study, then we observe individuals and we measure characteristics of interest, but we don't attempt to influence. So we're not applying any kind of treatment to the individuals, we're just observing. In an experiment, we are going to deliberately impose some kind of treatment so we can observe the response to that treatment. Another way to think of it is that in an experiment, like, the researchers are controlling, like, who's in which group, and in an observational study, they're just observing. So really the individuals are kind of selecting, you know, their preferences or what happens there. So here's an example. The Nurses' Health Study has interviewed a sample of more than 100,000 female registered nurses every 2 years since 1976. The study finds that light to moderate drinkers had a significantly lower risk of death than either non-drinkers or heavy drinkers. So is this an example of an observational study, an experiment, or is it uncategorizable without more information? And I have this fancy poll. Can you guys see the poll on your screen? Okay, so you can vote for your answer that you think it is in the poll, and then I'll see if I can show the results. All right, so you guys answered A, and that was absolutely correct. So this is an observational study because they're just asking these nurses questions. They didn't apply any kind of treatment. So it was the nurses who decided like how much drinking they were going to do. It wasn't the researchers who decided how much drinking they were going to do. So that makes it an observational study. Okay, so here's another one. A researcher has developed a new pain medication. He wants to see if it's better than Motrin or Vicodin, two commonly used pain medications. He finds 60 subjects who want to have their wisdom teeth removed in exchange for participating in the study. 20 subjects are randomly assigned to each of the 3 medications, and their level of pain is monitored. All right. Okay, so now can you see this poll again? You can go ahead and vote for what you think it is on this one too. Ooh, you guys are a lot more confident on this one. That was some fast voting on there. So you guys all guessed B, an experiment, and you are correct. So in this case, there is a treatment that's being applied. The researchers put the subjects into the different treatment groups, the Motrin, Vicodin, or the new study drug. So this is going to be an experiment. All right, so when we think about collecting data, we have some different methods of sampling that we can use that we talked about: simple random sampling, stratified sampling, systematic sampling, cluster sampling, and convenience sampling. And the two that most commonly get confused with each other, let's see back here, are the cluster versus the stratified. So in a stratified sample, we'll start with that one down here. In a stratified sample, then you take your population and you put like individuals together. So you can see in my picture here that all the blue people are together and all the black people are together and all the red people are together. So you have groups of like individuals. And then inside of that group, you're going to take a simple random sample. So we're going to take a simple random sample from the blue group. We're going to take a separate simple random sample from the black group. And we're going to take another simple random sample from the red group. And then we put all those simple random samples together, and that's what forms our stratified sample. So the cluster sampling method also involves grouping, which is why it's often confused with stratified. But the difference is that in cluster sampling, our groups within the group are not similar. So notice in this case, this group has blue, black, and red people, okay? And the Main Street group has blue, black, and red people, and the First Street group has blue, black, and red people. And in cluster sampling, we have lots and lots of clusters. So there's only 3 shown here, but there would be lots, like maybe 100 clusters. And we're going to take a random sample of clusters. So if your cluster is chosen, everybody in the cluster is going to be in the sample. Whereas in stratified, we have a very few number of groups typically, and we're just taking a handful of people from each group. In the cluster sample, we're sampling the entire group. So that's kind of a breakdown of those 2 methods. So I do recommend, like for all the different methods, I don't know if you watched the Skittles video that I posted a couple weeks ago, but I recommend going back and watching the Skittles video for the first time, or again, if you already saw it. because it has a very visual way of kind of breaking down these different methods of sampling to help you remember which one is which. All right, so here's an example. See if I can relaunch the poll so you can vote. A firm wishes to survey a sample of a large company's employees. The company has 100 managers, 1,000 laborers, and 300 engineers. They randomly select 5 out of the 100 managers, 50 out of the 1,000 laborers, and 15 of the 300 engineers to be in the sample. What type of sampling was used? So you can vote A, B, C, or D over in our poll. All right, so we were kind of split here between stratified and cluster. So the correct answer on this one is stratified. So they took their population of the company's employees and they divided them into groups of like individuals. So they had managers, laborers, and engineers. So in stratified, the groups inside the group, they're similar. So we had all the managers together, they're similar. We had all the laborers together, they're similar, and all the engineers together, they're similar. And then we took a sample from each of those groups. So only parts of each of those groups were going to be in there. So that's what makes it a stratified sample. All right, here's another one. I'm interested in finding out if students think that toilet paper should come over the roll, under the roll, or if it doesn't matter. I obtain a list of all BYU Idaho students. Using a random number generator found on random.org, I select 100 students. Out of the 100 students selected, only 85 can be contacted. So is this a simple random sample, stratified sample, cluster sample, or convenient sample? A, B, C, or D? All right, so majority of people put A, and A is the correct answer. It is a simple random sample. So what makes it a simple random sample? Well, in a simple random sample, you have a list of everybody in the population, and it's basically like drawing names from a hat. So you randomly select your sample from everybody. So that's what they did. They had a list of all BYU Idaho students, and they used a random number generator on random.org to select the 100 students that they wanted to participate in their sample. So a convenient sample is when you don't use a random method at all, you just do whatever is going to be easiest. So in this case, maybe you would just like ask all the people that lived in your dorm, or you know, ask everybody in your biology class, or something like that would be a convenient sample. Okay, so in this same example here, what are the population and the sample in this study? So remember, the population is the entire group of interest. I don't really have a good way for you guys to use hand signals to respond to this one, so I'll just talk about it. But so the population is the entire group of interest. So that would be all BYU-I students, because that's who we want to draw conclusions about, is students, all BYU Idaho students. So that's going to be my population. Now, the sample is going to be the subset of the population that we actually measure. So this one can be a little bit tricky in this scenario here, because we randomly selected 100 students, but only 85 could be contacted. So it's actually the 85 that are going to be our sample. We wanted the 100 students to be our sample. Those are the ones we randomly selected. But in the end, just the people that we actually measure are considered our sample. So the 85 that we actually were able to talk to, that's going to be our sample in this case. All right, so moving on to describing the data. The first way that we describe the data is going to be graphically. And if we have quantitative data, then one graph that we like to use is a histogram. In a histogram, we can see the shape, center, and spread of the distribution. And when we're looking at the shape of a distribution, typically we're looking for like symmetric, left skewed, or right skewed. So here's some data that I had. A student actually collected this and gave it to me. This was the top 100 NBA players in 2013. I only put 20 on here because that's all that fit on my slide, but the graphs are based on all 100 players. And you can see that it has like the player's rank, their name, what position they play, how tall they were, how much they weighed, whether or not they were on a playoff team. So here is a histogram of all of those players' weights. So I'll relaunch the poll again here. So looking at this histogram, what shape would you say this histogram is? Would you say it's symmetric, skewed left, skewed right, or other? All right, good job. So, so I would call this one pretty symmetric. So if you look at it, remember as a histogram, we're kind of trying to smooth out the general pattern of the histogram as we examine the shape of it, and it's essentially symmetric. So A would be the best choice for that one. Okay, so here is a histogram of the heights for those NBA players. So what shape would you say that the heights have? All right, awesome. You guys got this one 100% right. So this one has, which I thought was kind of interesting, that the weights were symmetric, but the heights look like they are skewed to the left. And remember, the skewness goes with the long tail, and you guys seem like you have this one mastered, but if anybody watching the video struggles at all with figuring out skewed right or skewed left, then I did post another video at the beginning of the semester that shows my memory trick that works really well for most people. Some people don't like it, but I've used that memory trick since back when I took this class when I was at BYU. So I like it. All right, question in the chat window says, how many bins do we use? That's a really good question. And there's not like an exact answer to that. You kind of just have to play around with it and see what looks good. So I'm trying to remember what the default number is in the Excel worksheet. I think it's like 8 maybe. So usually you kind of start with like between 5 and 8 and just try different ones until you can tell what the shape is. So if there's too few, then it just looks like a big clump. And if there's too many, then it can be too spread out. And it really just depends on the data that you have. But usually, 7, somewhere, I usually start somewhere around 7, and then I add some, subtract some till it looks like it's pretty good. All right, so here's some other data. This one, another student collected who ran the Denver Marathon, and she went around and asked people that she was running with how many weeks they trained, how many marathons they had run previous to that marathon. And she wrote down their gender, and then afterwards she wrote down their name so she could go in afterwards and look up their time at the end of it all. So this is their time in minutes that we have here. And what do you think about the shape of this one? This one is the time. So symmetric, skewed left, skewed right, or other. All right, we got a few different answers on this one. Overall, I would say that this is generally symmetric. it's not like perfectly symmetric or anything, but you kind of follow the overall pattern here, then it seems to be pretty symmetric. There doesn't seem to be any outliers on the upper side or the lower side, and it's generally clustered in the middle here. So I would probably call this one symmetric. Okay, next graph. This one is the number of marathons previously run. So would you call this one symmetric, skewed left, skewed right, or other? All right, 7 out of 7 of you voted, and you were unanimous in saying that this one is skewed right, and you're correct. This one's very clearly, we've got some gigantic outliers out here. I think someone had run 69 marathons previous to that, which totally blows my mind because I can't seem to get one marathon off my bucket list. I still haven't run my one marathon. I trained for one, but I never ran it. So I think this is amazing. These couple outliers that are out here that are like super duper tons of marathons that they've run. So clearly this makes this right skewed. All right, so once we look at graphs of the data, the next step is going to be to describe the data numerically. And there's two different types of numerical summaries that we typically look at. One is going to be a measure of center, and the other one's going to be a measure of spread. So first, if we look at measures of center, the main measures of center that we look at are the mean and the median. Sometimes you'll see the mode referred to, but that's not really a very good measure of center. So the mode is the most frequent value. So we pretty much, you don't really need to even think about that one because it's not one that's very good. But the two that are good are going to be the mean and the median. So the mean is the average, just add everything up and divide by the total. And the median is the middle value. So if you ordered them from smallest to largest and worked your way in from both sides, then the middle number is going to be the median. So in the median, then exactly half of the data is below the median and exactly half of the data is above the median. So when we have a symmetric distribution, the mean and the median are pretty similar, but when we have a skewed distribution, then the mean and the median can be quite different from each other. So with our marathon example where we had some definitely extremely skewed data here, you can see that there was a big difference between the median and the mean. And the mean is the one that's going to be pulled by the skewness. So the mean is going to go towards the tail or towards wherever the outliers are. So if the distribution is skewed to the right, then the mean will be to the right of the median. And if the distribution is skewed to the left, then the mean will be to the left of the median. So if you just remember that the median is like the stalwart one, it's true, it just stays in the middle, it's not swayed by outside forces, and the mean is just like, oh, you're an outlier, I'm going to come follow you, and it goes off that direction. So here's an example of the opposite where we have a left skewed distribution, and this was exam scores, and you can see, which are typically left skewed like this. That the median was 87, but the mean was 85. So the mean's going to be pulled towards these lower outliers down there. All right, the other thing that we look at is the variation or spread of the data. And some of the measures we use for that are standard deviation, variance, and the 5-number summary. So the standard deviation is just the square root of the variance. Those are mathematically related there. And typically we use the standard deviation when we're describing a set of data because it's in the same units as the data, so it's a little bit easier to understand. But if you look at my two pictures here, A and B, you can see that B has more variation. It's more spread out than A. So B would have a larger standard deviation. And if you look at the dotted line for where the mean was, you can see that that B would also have a higher average or than A as well. And one way that we kind of look at spread is by using a box plot. A box plot is a graphical look at the 5-number summary. So all the different 5 numbers of the 5-number summary are represented on a box plot. And note that the mean is not on a box plot, so you can't tell the mean from a box plot. You can only tell the 5 numbers that are in the 5-number summary. And using the box plot, you can use the box plot to figure out what those numbers are. Okay, so if you just take your graph here and just kind of extend the line over, then like if I wanted to know, what the median was here, then I would just kind of keep extending the line of that median all the way over to the axes, and then I would be able to estimate what the median is. So just one thing I want to say about this is that just be careful and make sure you draw the line over. There may or may not be a question on the test where you might have to answer a question like this, and the biggest mistake that I see is people just kind of eyeball it, like they would look at this median and say, oh, it's 300, okay? But if I actually extend that line over, then you can see that it's not 300, it's a little bit less than 300. So if I was kind of eyeballing this, I'd probably call that like 295, which would be in the realm of there's a little wiggle room on these kind of things. But 300 would be outside the wiggle room. So just make sure that you actually carry the line all the way out to the axis, if that makes sense. There's my test tip for you. Question in the chat window says, when there's a dot outside the whisker, is the line still the max, or is the open dot the max? That's a good question also. And actually it's the open dot that is the maximum. So whatever is the last thing. So she's saying, okay, if there was a line, but then there was a dot out here, some software programs try to indicate where outliers are by making them dots or stars instead of continuing that line all the way out. But if there is a dot or star, then that would be the maximum or minimum if it's on the other side. All right, and going along with the box plots then, because we're talking about the 5-number summary, the 5-number summary divides the data into quartiles, into 4 equal parts, meaning that there's going to be 25% of the data in that first quartile, there's going to be 25% in the second quartile, 25% in the third quartile, 25% in the last quartile. So let's see. Looking at our picture here, let me pull the poll back up again. What percent of the data is going to be between 258 and 329? All right, we have some split answers on this one. Okay, so 258 is right down here, and 329 is our maximum way up here. So if we look here, we know there's 25% in that top quartile. There's going to be 25% here between Q3 and the median, and another 25% here between the median and Q1. So if I add those together, 25 plus 25 plus 25 means that C is the correct answer. We're going to have 75% of the data that is between 258 and 329. All right, so moving on to probability. So we talked about doing two different types of probability. So one was for discrete distributions, and a discrete distribution is when you have a finite or countable number of outcomes. Basically, if you can sit down and make a list of the possible outcomes, then it's going to be a discrete distribution. And if you sat down to make that list and you were going to be there for the rest of your life because there was an infinite number of possibilities, then it's going to be a continuous distribution. So when we have discrete distributions, then we can just use our probability rules to answer questions about that distribution. So here's an example. If you draw an M&M candy at random from a bag of candies, the candy you draw will have one of 6 colors. The probability of drawing each color depends on the proportion of each color among all the candies made. Assume the table below gives the probability that a randomly chosen M&M has each color. And I have to say this example makes me kind of laugh a little bit because it includes tan. So clearly this is some old data, because who remembers tan M&Ms? You have to be like my age to or older to remember the tan M&Ms. That seems like it was a long time ago. All right, so first question says, what's the probability of choosing a yellow M&M? So looking at my chart here, the chart is saying, okay, probability that I draw brown is 30% or 0.3. The probability that I draw red is also 30% or 0.3. Green, 0.1, orange, 0.1, tan, 0.1. And this is a probability distribution, and I know, according to my rules of probability, that if I add up the probability of everything in my, of all possible outcomes, then it always has to add up to 1. So I know that the total of all these has to be 1. So if I know that, then I can find the missing number just by adding up everything else and then subtracting that value from 1. So I'm going to have 1 minus the sum of 0.3 plus 0.3 plus 0.1 plus 0.1 plus 0.1. So adding all those up together, I get 0.9. So I take 1 minus 0.9, which gives me 0.1. So the probability of yellow then is just going to be 0.1 or 10%. And just make sure on your exam that you just read the instructions as far as how they want you to enter in the probabilities. Most of the time they're going to want you to enter them in as a decimal, but every once in a while they throw something at you where they want you to do it as a percent without the percent sign, which is not the decimal form. So just read the directions on those. Next question, what's the probability that you do not choose a red M&M? So if I want to know the probability that something does not occur, so the probability of not red, then the probability rules say that it's going to be 1 minus the probability that I do get a red. So red here is 0.3. So the probability I do not draw red then would be 1 minus 0.3, which is 0.7. So the probability that you do not choose red would be 70%. And then final one, what's the probability of choosing a green or a brown M&M? So again, our probability rules say that if we want to know the probability of A or B occurring, so in this case, green or brown occurring, it's just the sum of the individual probabilities. So the probability of green plus the probability of brown. So in this case, green was 0.1 and brown was 0.3. So I can add those together, 0.3 plus 0.1. So the probability of brown or green would be 0.4. All right, so moving on to continuous distributions. So remember, continuous distributions is when, if you sat down to make a list of the possible outcomes, that you would be there forever because there's an infinite number of possibilities. So because there's an infinite number of possibilities, we can't assign probabilities to the individual outcomes because there's too many. So instead, we use density curves to determine the probability, and we calculate probability by finding area under the curve. And there's lots of different density curves out there that can be used to find probabilities. But in our class, we pretty much focus mostly on the normal distributions. So the normal distributions are those lovely single-peaked, symmetric, apparently mine's falling off a cliff, it's all sideways, distribution. And the reason why we focus so much on normal distributions is because there's a lot of data in real life that actually follows a normal distribution, which makes these very useful, very useful density curves. So to find probability, like I said, we're just going to look for area under the curve. So if we have a normal density curve, the way that we're going to find area under that for our class is we're going to standardize. So in other words, we're going to find the z-score, and we're going to use the normal applet to help us find the area, since pretty sure none of you guys know how to integrate the normal distribution function to find the area that way. The applet's much easier and very visual. I like the applet. So here's an example. A professor knows from past experience that the time for students to complete a quiz is normally distributed with a mean of 21 minutes and a standard deviation of 3 minutes. If he allows 25 minutes for the quiz, what's the probability that a randomly chosen student will not complete the quiz? So again, probability is just area under the curve, and in this case, we're told that we're looking at a normal curve because it says it's distributed normally. So in order to answer this question, we're going to standardize and use the applet to find the appropriate area. So first step is going to be to standardize. So we find the z-score by taking x minus mu divided by sigma. So in this case, the x is given here in the problem, 25 minutes, and then mu and sigma are also going to be given in the main scenario of the problem. So our mean mu is 21, and standard deviation sigma is going to be 3. So we take 25 minus 21 divided by 3, which gives me a z-score of 1.33333 repeating. So a z-score, when we say we're standardizing, we're kind of changing the units of measure. Instead of measuring in minute units, now we're going to be measuring in number of standard deviations away from the mean. So the z-score tells you how many standard deviations your value is from the mean. So 1.33 would say, hey, 25 minutes is 1.33 standard deviations above the mean. So in the chat window, there's a question. It says, will we be able to ask questions about the preparation assignment review questions? Sure. Yeah, you can ask questions, all the questions you want at the end of the main part of the review. All right, so next step is I go to the applet. So remember my z-score was 1.33. So I plug in 1.33 down here for my z-score into the applet. And if I back up to my question here, we wanted to know the probability that the student would not complete the quiz. So if they don't complete the quiz, that means it took them longer than the 25 minutes to complete the quiz. So because we're looking for longer, which is greater than, then we're going to shade this upper, shade the area to the right. So greater than is to the right of your z-score, and then less than is to the left of your z-score. So, so it's positive, I entered it on the right side. We wanted to know the probability of longer than, so we shaded that, just that part. And the other z-score thing over here, we just ignore it because we only needed the box on the right this time because we had a positive z-score. So once we've done all that, then the area is going to be our answer. So probability is just area under the curve, and there it is, our area. So 9.0913 would be the answer that we would enter in for the test, or approximately 9.13%. Okay, so here's another example. Same scenario about the professor knowing that the quiz is normally distributed with a mean of 21 minutes and a standard deviation of 3 minutes. Suppose that he wants to allow sufficient time so that 95% of students will complete the quiz in the allotted time. How much time should he allow for the quiz? Or in other words, what is the 95th percentile for this distribution? And this is probably more like the way that they word it like in your textbook or on the exam, is asking for the percentile here. So in this case, this is a backwards problem because they're giving you the percentile, and your answer is going to be a quiz time. It's going to be an X value. So because it's backwards, then we do everything in reverse. We start with the applet, and then we end with the z-score formula. And just a note, a reminder of what percentile means. If you're in the 95th percentile, then that would mean that 95% of the observations are below you. and hence 5% of the observations are above you. I already said that part. Okay, so in the applet, on these backwards problems, then it's a good idea to shade first, because sometimes once you start entering things in, you might not realize that numbers are changing in other parts of the applet. So if you shade first, then that eliminates that possibility for error when you unshade things later and it ends up changing numbers in the area box and you didn't realize it. And so always shade first. So how do you know how to shade? Well, if the percentile is less than 50th, then shade the left tail. And if the percentile is greater than the 50th, then you're going to shade the middle and the left section. So in this case, our percentile was 95th. 95th is greater than 50th, so we're going to shade the left and the middle section for this one. Once you've shaded correctly, then you input the percentile. So we had the 95th percentile, which in decimal form is going to be 0.95. So we put that in our little area box. And once we've done that, then we're going to write down the z-score. So the z-score that I need in this case is 1.645. All right, so I take that z-score back to my z-score formula. So remember, z-score formula was z is equal to x minus mu divided by sigma. So now I know z, I just got it from my applet. Mu and sigma are going to always be given to you, and x is what you're trying to find. So I plug in everything that I know into the z-score formula, and then I can solve for x. So solving for x in this case would give me 25.935. That would be my 95th percentile. So in other words, about 95% of the class is going to finish the quiz in about 26 minutes or less. And here's just a little hint, like if you don't, this is the way that I like to do it. I like plugging it into the formula and solving every time, because to me, I like working through the logic of why I would do that. But if you don't like doing the algebra every time, you could actually just do the algebra one time, which has already been done for you here. And you could use this formula and call it kind of your backward normal formula. So in this case, this has everything that you're given on this side, because we're going to find the z, you're going to be given sigma and mu, and then you can solve and it'll tell you what x is. So, so if you wanted to write that one on your cheat sheet, if you like it better, you could do that too. All right, going along with normal distributions, a QQ plot is one way we can tell if our data is normally distributed. So there's lots of instances when we're going to need to know whether or not our data is normally distributed. That would, for one thing, it would help us know whether or not we could just use the normal distribution to answer questions about that distribution. And then later it's going to be a requirement for some of the procedures that we're going to do. So to figure out if a data is normally distributed using a QQ plot, a QQ plot basically plots your data on a special kind of graph paper that is made, the graph paper is made in such a way that if the data is normal, then the data will fall on a straight line. And if the data is not normal on that special graph paper, it will not fall on a straight line. So looking at these three graphs here, then hopefully you can see that this first one here, these points, they mostly fall on that line, and when they're not on the line, they're just kind of randomly on either side of the line here. So they fall pretty close, kind of bouncing back and forth on both sides of the line. Both of these other ones here, you can see some distinct curvature in this one here, which makes it not normal. And then you got kind of an S curve going on this one, which also makes that one not normal. So, and if you struggle at all with reading QQ plots, there was a link I sent out, I believe it was the same time that I posted the video for, I think it's lesson 5 when I talked about normal distributions. So if you scroll back through the announcements on iLearn, you could find the link. But there is a really good link on there that kind of went through how to interpret a QQ plot. But if you just remember that straight line means normal and then not straight line means not normal, then that'll do it for you. And I feel like I felt like there were some in the homework that were kind of iffy, but I feel like the one, if there is one on the exam, I feel like it's pretty obvious. I mean, I don't think it's like a fence sitter. I think it's pretty clear. All right, then finally we get to the last unit that we just recently been discussing, and that is this idea of, okay, we've been looking at individuals, but what happens when we look at sample means? So we're taking a sample, and we might want to know how that sample mean is distributed. So when we're looking at probabilities for individuals, we use the population distribution, and that's what we've been talking about so far, really. The mean of the population is mu, the standard deviation is sigma, and the shape of the population could be anything. It's whatever distribution the population has. We've, in the last two lessons, really, we started talking about looking about probabilities for sample means, and to do that we use what we call the sampling distribution, or the distribution of the sample mean. So sampling distribution and distribution of sample mean are the same thing. And basically what the sampling distribution is it's the distribution of values taken by X bar in all possible samples that we could get from that population. So when we're talking about the distribution of the sample mean, we're not talking about looking at individual values. We're not talking about looking at the population, but we're talking about looking at a sample of individuals and calculating the mean of that, and how would different sample means be distributed. So the sampling distribution, if you take the mean of all possible sample means, it turns out that value is equal to mu. So the center of the sampling distribution is the same as the center of the population. The standard deviation of the sampling distribution is equal to sigma over square root of n. So this is pretty important here. And then the shape of the sampling distribution, well, we discovered that if the sample size is large, then, which in our class we say large is 30 or more, then the sample mean will be approximately normally distributed. So note that this doesn't change the shape of the sample or the population. Those are individuals. They're going to have whatever shape that they have. We're talking about the distribution of the sample mean. That's what's going to be approximately normally distributed. So as we started talking about the distribution of the sample mean, then there was two kind of ideas or theorems that we talked about, and these two can be really easy to confuse with each other. So I'm just going to talk about both of them and kind of point out the differences between the two. So one we talked about was called the law of large numbers, and the law of large numbers said that as your sample size increases, then the mean of the observed values is going to be closer and closer to mu, the mean of the population. So it says if n is large, then X bar is close to mu. And the other one we talked about is the central limit theorem. The central limit theorem says that if n is large, then the distribution of sample means will be approximately normally distributed. And you know, we said 30 is kind of the rule of thumb that we use in our class for how large is large. So looking at these, the law of large numbers is about the sample mean. It says sample mean close to population mean. Okay, the central limit theorem is about the shape of the sampling distribution. So the central limit theorem says that the sampling distribution will be normal. So the distribution of sample means will be normal, even if the population itself was not normal, if your sample size is large. So both of them say, as an increase, you know, both of them talk about sample size being large, which makes them easy to confuse with each other. So if you just keep in mind that, you know, law of large numbers says X bar close to mu, central limit theorem says X bar is going to follow a normal distribution. And these are pretty important concepts. And all of our exams are cumulative in here. So this is something that I would recommend that you write down on your cheat sheet, or kind of keep in mind for this test and all future tests, because there's very likely to be a question about either or both of these on this exam and future exams. All right, so when we're talking about finding probabilities, if the population is normal, then we can use the z-score and the normal applet to find probabilities for individuals. So that basically was just like the examples that we just did with the quiz scores. And if our sample size is large and we're looking at a sample, then we can use the z-score and the normal applet to find probabilities for sample means also. So the trick is in the wording of the problem. You really have to pay attention to how the problem is worded. If we're looking for probabilities about individuals, then we use the individual's z-score to find those probabilities. If the probability is about a sample mean, then we're going to use the z-score for sample means, which includes that extra square root of n down there to answer those questions. So here's an example that kind of highlights the difference between how those questions might be worded. So this one says, light vehicles sold in the United States must emit an average of no more than 0.05 grams per mile of nitrogen oxides after 50,000 or fewer miles of driving. NOx emissions for one car model vary normally with mean 0.03 grams per mile and standard deviation 0.01 gram per mile. A says, what's the probability that a car of this model emits more than 0.05 grams per mile of nitrogen oxides? And B says, a company has 25 cars of this model in its fleet. What's the probability that the sample mean of these 25 cars is above 0.05 grams per mile? So looking at these two questions, you can see the difference between what they're asking here. So the first question is asking about a car. So a car is an individual. So to answer this probability question, we would use the z-score for individuals, which is just the x minus mu over sigma. This second one says, hey, we have 25 cars. What's the probability that the sample mean of those 25 cars is above the 0.05? So because it's asking for probability about a mean, we're going to use the z-score for sample means, which is the x bar minus mu over sigma over square root of n. So we'll work through those. But you see the difference between the way that the questions are asked. So it's a good idea, like read the questions on the exam really carefully and say, okay, is this asking for probability for an individual, or is this asking for probability about a sample mean? So here's the first one. What's the probability that a car of this model emits more than 0.05 grams per mile of nitrogen oxides? So this one is asking for probability about an individual. So we just use the population distribution. So the mean of our population was 0.03. The standard deviation of our population was 0.01. And the shape of our population was normal because it said so in the problem. So we would do the same steps that we talked about before. We're going to standardize, meaning calculate our z-score and use the normal probability applet. So the x value that I'm interested in is that 0.05, because that's what it was specified in the problem here. And I subtract the mean and divide by the standard deviation, gives me 2. So then I would plug that into my applet. And we wanted to know more than, so that means we're going to shade to the, where did my pen go? Shade to the right here, put in my z-score, and then I get my area of 0.0228. So the probability that a single car of that model is going to have more nitrogen oxide is than 0.05 is 2.28%. Looking at the other question said, what's the probability that a sample mean of 25 cars is more than 0.05? Now we're talking about probability for a sample mean, so we have to use the sampling distribution or the distribution of sample means. So the mean of the distribution of sample means is equal to mu. So that's going to have the same value as we did in the previous problem. But the different one here is going to be the standard deviation. So again, look for wording on the exam. Is it asking you about standard deviation of a population, or is it asking you about standard deviation of a sample mean? So if we're talking about the distribution of sample means, then we're looking at sigma over square root of n. So sigma was 0.01, but our sample size was 25. So if we take 0.01 divided by square root of 25, we get 0.002. So that's going to be the standard deviation of the sample mean. And the shape is going to be normal because the original population was normal. So that means that our sample mean is also going to be normal. So again, we can find the z-score, but notice this time that I'm using the z-score for sample means, which the big difference there is that I'm going to have that square root of n in the denominator. So, and clearly I'm harping on this a lot because this is like one of the most common mistakes that's made on this exam is just using the wrong formula. So forgetting to do that square root of the sample size down in the denominator when we're doing probability for a sample mean. So I get a z-score of 10 there, which is gigantic. And I'm looking for more than still. So I'm going to shade everything to the left, but there's not much area out there to the left. And in fact, when I plug everything in, then I get essentially 0. So the applet, after you start getting really, really small, it starts doing things in scientific notation. So this is saying like 7.6 times 10 to the negative 24th, which means that I'm going to have 23 leading zeros before that 7. So in other words, this is like an itsy bitsy teeny weeny number, essentially 0. So the probability that a sample of 25 cars would have a sample mean that is more than 0.05 is nothing. It's practically 0. All right, so we're kind of up on our hour here. So these are just some other things that I would recommend going back and looking at before you take the exam. So I'd go back and review the 5 steps of the statistical process. Just make sure you know what you do in each of the different steps so that if they told you, hey, you know, we're doing this, which step is this, that you could say, oh, you know, that's the design phase, or that's the collect the data phase, or whatever. Go back and look at the 68, 95, 99.7 rule. If a problem on the test says to use the rule, then do not use the applet or you'll get the question wrong, okay? If it says to use the rule, then you should be able to do the problem just using the rule and without using the applet at all. And if you're struggling on that one, and I mentioned this back down here again too, but go watch the normal distribution video that I posted. I think it's lesson 5 that I posted it with earlier. Just scroll back through the announcements. The link is in there because the first half of the video talks all about the 68, 95, 99.7 rule. Make sure you review how to calculate summary statistics in Excel using the spreadsheet that we used in class, that quantitative descriptive statistics spreadsheet. So you'll probably be given a data set on the exam and they're going to ask you, hey, what's the mean? What's the median? Or what's the 75th percentile? Or some of those kind of things and that you should be able to answer using that Excel spreadsheet. And then I already mentioned both of these, but I recommend rewatching the Skittles video on sampling and rewatching the normal distribution video that I made back by lesson 5. So that's all that I have. So now I'm happy to answer like any questions that you guys have. Does anybody have any questions?